So confidence interval. So far we have done what we can call it as point estimation. We have given a single value as estimate of the parameter. So for example, we get a y bar and we say that that's a estimate of the parameter capital Y hat. So that's an estimator, but that's one value. So that's a point estimation. But we can also give an internal estimator in the form of lower y comma upper y, such that the true value of the parameter lies in this interval with a certain predetermined probability. So we are giving this interval such that the true value of the parameter lies in this interval with a predetermined probability. We say 95% probability, but the way we call it is 1 minus alpha. So 1 minus type 1 error, which we set as 0.05, for example. That will give us a 95% probability. So what is the definition of confidence interval? Definition of confidence interval is a confidence interval for a parameter theta with confidence interval 1 minus alpha is an interval lower y upper y such that the probability that theta lies in this interval is 1 minus alpha. So if we do the calculation and we find out that 95% confidence interval of a population mean is 2.36, 4.89. What does that mean? What that means is, if we take a large number of repeated samples and then from each sample we calculate 95% confidence interval or interval endpoints, then 95% of these intervals will contain the unknown population mean. So that is the actual definition of the 95% confidence interval. So now we have taken a bunch of samples from a population and we use this to find an estimator theta 0. For example, we using it to find the population mean. So there would be a bunch of theta zeros from different samples. So what we have learned before is that we can approximate that these theta i's are normally distributed. Now if these theta i's are normally distributed, they are going to have a mean of theta. Why? Because the theta I is a unbiased estimator of theta hat is an unbiased estimator of theta, and that is why the expected value of theta hat is going to be theta. Expected value of theta hat is nothing but the mean. So that is why if all these theta hat i's are normally distributed, the mean is going to be theta. And now we say that it has a standard deviation. Standard deviation here is nothing but standard deviation of theta hat. This is not the standard deviation of the individual sample. This is the standard deviation of theta hat. And we also don't know it, so we estimate it from the sample. So that's also a hat. We ideally want to have a population of here, but we don't have it. We're not going to take multiple samples, we just take one sample to calculate it, and that's why it's a theta hat. So then how we calculate the 95% confidence interval? So if this is theta and say there is an upper limit, a u and an l, what's u going to be if this is a standard normal distribution? If it's a standard normal distribution, u is just going to be, actually this value is going to be u divided by sigma theta hat is going to be the z value, and the z value would depend on the 95 the confidence interval limits. So we can say 95%. If we know 95%, then we know that this value is going to be 1.96. So z becomes, and we're gonna take 95%, we're gonna take half, because this and this, if we just take 95%, then it's going to be, value is going to be different, but we typically take it as this can be upper and lower, and that's why it's z half. And then u is nothing but z half times sigma hat theta hat. So that's your upper u, and the same thing is going to be with the L, which is going to be z half sigma hat theta hat. And that is why the confidence interval is going to be theta hat minus z alpha half sigma hat theta hat comma theta hat plus z half sigma hat theta hat. And what the value of z half is going to be, it's going to be dependent on the confidence interval chosen. So confidence interval 1 minus alpha, we can choose 90%, 95% or 99%. Typically we choose these, and value of z half alpha is 1.64, 1.96. This is typically what you're going to use most of the time. That's 95% confidence interval, and 2.58. And this also shows this, that the more tighter the confidence interval, higher the confidence level, we are using 99% confidence level, the length of this will become more. So we are 99% certain that the parameter is here, so obviously the interval length is going to be bigger. But this whole process is only applicable when the sample size is large. If the sample size is small, then we have to use the student t-test and use the student t values instead of the z values that we have placed over here. Okay, so that's basically how we do the confidence interval calculations. But now let's move on to see the confidence interval of population mean under SRSWOR. In this case, what we have is the population theta is population mean y bar for a sample of size n by SRSWOR. Now, if the estimator from this sample is y bar and its standard error is small y bar, then the confidence interval is given by this equation, which is y bar minus z half big S. This will be big S, yeah, upon under root n 1 minus f y bar plus z half big S upon under root n 1 minus f. So what is this whole thing? This whole thing is nothing but the standard error of y bar or sigma y bar, that is s upon under root n 1 minus f, and that we have learned before is how you calculate the sigma of the sample mean. So we can do a question. For example, we have a population n of 720 and we have a sample of 64 and we got a sample mean of 142.4 and sample standard deviation is 108. Now we want to calculate the confidence interval in this case. So with this sample standard deviation, we're going to substitute here instead of the population standard deviation, and then we just going to do 142.4 minus 95% confidence interval, so the half is going to be 1.96. we're going to put 108 here under root 64 and then 1 minus f. F is nothing but n upon capital N, so small n is 64 and the big N is 720, and that will give us a number of 25.25. So this S here is supposed to be the standard deviation of the population, but since we don't have that, most of the time we substitute it with small s. Similarly, if we want to know the population total, if the parameter theta is not the y bar but y itself or y hat, then all you do is to multiply n with it. So you multiply n with this and you multiply n with this, and that will give you the total y's. Now the next is going to be the confidence interval of a proportion. How do we calculate that? So when population can be classified into two classes. So suppose we have a population and we can classify that population into two classes, say class A and class AC. So the proportion P of units falling in A can be estimated by the corresponding sample proportion small p, right? So we know that the variance or estimated variance of p is p that is equal to pq upon n minus 1 minus f, and sigma hat p is going to be under root pq n minus 1 times under root 1 minus f, and this is just the variance of a just a proportion that we are trying to calculate. So how will we calculate the confidence interval then? That is less than p 1 minus z half under root pq n minus 1 minus f plus 1 upon 2n. Now this thing is a correction of continuity. This is because we've all calculated this all by using a normal approximation. So because of this we have to use this correction factor here, 1 upon 2n. And if we want to obtain the only when if the p is very less, or the proportion of units falling in class A, for example, is less than 0.05, then we should not, so it has to be 5% or more, then only we can use this sort of a normal approximation to calculate the confidence interval. Sometimes things get a little complicated, and we have instead of 2 classes we have 3 categories. So here it actually looks complicated, but it isn't. For example, let's say that there are k possible categories, and ai and ai are number of units in class I. So what would be the n? N is just going to be the sum I is equal to 1 to k ai. And why is that? AI is not here the A and AC. AI is the total number of units. So for example, we have these 3 buckets, right? 1, 2 and 3, and the number of units are say A1, A2 and A3, and the other, for the example is we are asking a question and some people say yes, some people say no, and some people say NA. So the total number of people who responded is going to be the sum of this AI, and so N is just going to be A1 plus A2 plus A3. Now PI, or the proportion of patient in A, is just going to be A1 upon N, and the small pi which we are getting from sample is going to be AI upon small n. Now as long as the sample size, the n, is small compared to number of units in each group, as long as the A1, A2 and A3 are good number and n is small. So for example, you have a total population of 1000, and out of this population A1, A2, A1 is 500 and A2 is 250 and A3 is 250. So if you take a sample n of 250, then this normal approximation will not work. But if n you are taking as 40, then you can use a normal approximation to get the confidence interval. Sometimes, and most of the time, we are only interested in either one proportion. So for example, we might only be interested in a upon n is the p, is the capital P, and the small p is a1 upon n, and that is all we want to calculate. Or we can have a situation where we are interested in a1 and a2 upon n, and p is equal to a1 plus a2 upon n. So we can use the same confidence interval formula. Or there is another thing we can do, is we can ignore this completely. We can say that we're going to ignore this whole thing completely, and then p will just be a1 upon a1 plus a2. In this case, we have an n dash, which will be a1 plus a2 only, instead of a1 plus a2 and a3, and you can use the same formula using n dash. So again, we're getting three types of responses in a survey, and we compute p as a1 upon a1 plus a2. Then, even though a1 plus a2 plus a3 is equal to n, our effective sample size is going to be n dash, which is just a1 plus a2. Then you can obtain the confidence interval here, which is just going to be p plus minus z half underscore pq n dash minus 1 multiplied by 1 minus n dash upon n dash plus 1 upon 2 n dash. Now again, we need this, but we don't know this, so we're gonna just substitute it with n upon n, even though this may not be entirely accurate. So one question we're going to do is, we have a simple random sample of n is equal to 100. We obtain from n is equal to 500, and the proportion number of people who answered yes and fall in the category A is 37. So no is going to be a complement of this, which is going to be 63. We want to calculate the 95% confidence interval for the proportion of units in class A in the population. So now, in a situation like this, we already know the p is equal to 0.37. We just need to calculate the confidence interval. So this is going to be z half pq n minus 1 minus f plus 1 upon 2n. So this is going to be 1.96 under root 0.37 times 0.63 divided by 99 multiplied by this whole thing is not a this whole thing is not this is just so 1.96 times 0.36 multiplied by 1 minus 100 over 500 plus 1 upon 200. So that will give us a number. So it will give us 0.37 plus minus 0.89. But if you want to do a 95% confidence limit, this is not the right answer, right? You have to then add to this and subtract to this. So the 95% confidence interval is going to be 0.28 and 0.45. So this is the proportion. Even though from this sample we have calculated this, not only we are able to calculate this, but we don't actually know what the population is going to be. So then we have this, because all we need to calculate the population really is the is sigma, but not the sigma of the sample, sigma of the distribution of the y bar of the sample. So this is sigma y bar, and n it's an estimator, because the real sigma y bar or standard error would require the population p, but we don't have the population p or q, so we are just estimating it, and that is why we get this number. And this is all there is to it, to calculate the confidence interval. And the whole idea of being able to calculate this confidence interval is that all of this can be assumed to be a normal approximation.